All right, welcome back. Happy Monday. How's it going? Good, 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 good. Looks like homework 3 got finished okay. Do you guys want to go over the end part of that at all? Yes? Mm-hmm. Sure, I would be happy to. So homework 3 questions. Or no, homework 4 that was, right? That was 4, sorry, I'm behind. 5 is not up yet, so right now you have nothing to do on your plate. Isn't that a beautiful feeling when it's on someone else's plate, just for that one brief shining moment? But never fear, you can be reading chapter 6. There's always something to do. So yes, I also updated your quiz points and homework points, so all of the points should be updated except for the 2 of you who turned in your quiz like within the last couple hours. You guys, I'll do yours later, but so yours aren't quite ready yet. Okay, so yes, this part was, can you find the right number on the output? Troubleshooting a couple of questions, by the way. I'll go through the whole, I'll get to you, I promise. I'll ramble for a minute or two first, as I'm prone to doing. More generally, if in your homework you get the right -2 log likelihood, that means you have the right model and you have the right estimator. If you can't get the right intercept estimate for the fixed intercept or intercept variance, what that means is that you haven't centered your predictors correctly. So just for future troubleshooting purposes, if your intercept is off but everything else is right, that means that you haven't centered your predictors. So in this case, this would happen if you used the week variable as your time variable, which was scaled 1 to 6 instead of time that was scaled 0 to 5. So I've had a couple different people run into that problem, so I thought I would point that out for your reference. And so all of these went reasonably well, and so your question was about section 4? Okay. So assuming linear change, enter the test statistic for whether each person needs their own linear effective time. Is that the one? Or is there one before that? That one? Okay. The second set. So 55 and 56 were okay. So that one, what am I asking about? Folks, what does it mean when I say whether each person needs their own linear effective time? What's the magic word that goes with that idea? Random, yes. So assuming linear change means we're talking about comparing a fixed linear change model to a random linear change model. And if the model with the random slope fits better, then each person needs their own slope or a variance of the slopes. And so the test statistic there is the -2 log likelihood difference. The exact p-value you should get correct if you have the right test statistic, assuming how many degrees of freedom? 2. That's the tricky one. You think 1 because you've added a random slope, but you've also added its covariance with the intercept in doing so, so it's 2. Then the next one, assuming a random intercept. So that right there tells you that the variance sides of these models are going to be the same. So the 2 models to be compared, each is going to have a random intercept on the variance side. Enter the test statistic to examine whether a linear trend adequately describes the means over time. So the 2 models to be compared then. Linear trend, we know that's a fixed linear model, right? Because we said assuming a random intercept, so it's not the random linear version, but the fixed linear version. Adequately describes the means. Which model gets you the original means? Saturated means. Now I say original in the sense that if you had complete data, they would literally be the same means as if you just ran them through descriptive statistics. If you have incomplete data, they are the means assuming missing at random. So they're not always going to be the same, but they are the ones that the model is trying to recreate. So then we have fixed linear versus saturated means, both with the random intercept. If The models to be compared differ in their mean side, the fixed side, which is the only estimator that you're allowed to use to compare those models. That's an ML. You cannot use -2 log likelihood under REML to compare those models. However, I'm going to teach you today, or perhaps on Wednesday, we'll see how far we get, how to get the same idea when you're in REML, because you don't want to switch back and forth across estimators if you don't have to. If you're in restricted maximum likelihood, odds are good you need it because of your sample size. You don't want to switch to ML in order to do certain comparisons. So I'm going to show you how to trick the model into doing that test for you and staying in REML. But for now, that would be fixed linear versus saturated means, both with a random intercept using maximum likelihood. All right, does that help? Or do you see, do you want to hear any of that again or said differently? So I'm quite certain you're not the only one thinking this right now, by the way. This was like the #1 question I got from people, so. We're doing a model comparison, but it's a different set of models. The same -2 log likelihood, although this time it's using the -2 log likelihood under ML instead of REML. Whereas 55 and 56 would have been REML, because you could do it in either one, and the instruction said if you can do it in either one, do it in REML. The difference is that in 55 and 56, the models to be compared differ in their variance side, not the mean side. So the mean side both has fixed linear. One only has a random intercept, whereas the other would have the random linear. So both likelihood ratio tests, different estimators. Would it help if I wrote it out briefly? Yeah? Okay. Let me do a little Excel thing here. So the whole sides of the model thing is a new concept because this has never occurred probably in any of your classes, but it's super important here to keep track of what you're actually talking about. So mean side, and I say fixed effects, broadly construed. That's one side. And then we have the variance side, and then the random effects, and the residuals. So the first question then, here we go. The first question then was asking about whether people needed their own effective time. So the models to be compared then would each have a fixed intercept. Fixed intercept, fixed linear time slope. They would, we're not counting residual variance because it's always there, so that's not in my chart. Random intercept, and then the question would be random linear time question mark. So it's that last cell that differentiates the models to be compared. They should be the same, other than one model has the random linear time slope and the covariance with the intercept, and one model doesn't. So these models differ on the variance side, the one that's in italics there. Therefore, they can be compared using ML or REML. And when that is the case, REML is preferred because that's the version that gives you better variance components in smaller samples. The other question then, both models had only a random intercept. I'm going to write it out like this here and list the models explicitly. The model with fewer parameters had actually fixed intercept and fixed linear time. Here, I move this down one more. And this one had saturated means. So what does that actually mean? It means you still have a fixed intercept plus 5 mean differences. Diffs, we'll call it like that. since it was 6 occasions in the homework. So this is one model to be compared. This is the other. In this case, they have the same variance side, they differ on their mean side. So right off the bat, we know it has to be an ML comparison if you want to do this via -2 log likelihood. What I'm going to show you today is how to do the same thing without a -2 log likelihood test, how to do it via a multivariate wall test instead, which basically means adding stuff to the model until you get to something that's equivalent to saturated means. So saturated means has fixed intercept plus 5 differences. This model up above still has the fixed intercept, but what it's saying is that those 5 differences can be approximated by a line. The differences are equal. So to the extent that the differences between occasions are not equal, a straight line isn't going to approximate them, and the model's not going to fit as well. So how many degrees of freedom for that model comparison to answer this question? Does the line fit the means? 4. 6 versus 2. Is that better? Was it hidden there? Okay. And I am streaming, so I will remind you that you can always go back and hear whatever you want to hear again, as well as read it again. The last questions then should be fairly self-explanatory because they were designed to make you pay attention to the numbers you had entered and see the tendencies. So which is true about random intercept variances? They will be bigger in REML than ML. Once you hit enough level 2 units, somewhere around 100 or so-ish, depending on how many predictors are in your model, the difference stops mattering. But whenever you're under that sample size, REML is going to give you better variance estimates. The ones from ML will be too small. Same is true for the random slopes. So any random effect variances are going to be better estimated in REML. They will be too small in ML. Given the same model, the estimates for the fixed linear slopes are the same. It's the same model. The standard errors, though, is the part that differs. Because, let me see here, fixed linear slopes, given the same model, the standard errors are going to be smaller in REML than ML, right? Bigger than, excuse me, thank you, bigger than REML than ML because of the variances. And given the same estimator, they will be bigger if the slope is random than fixed. And the confidence intervals are wider in REML than ML because the variances are wider. All right. Okay. Other questions on that? Okie dokie. Well, let me know if you think of anything else. Otherwise, we will move on. Lecture 6 and example 6, which previously had been 4 separate examples, and I put them together because they're all using the same data to create what I think is a personal record in terms of handout length. I think so. Let me find it. Yeah, 39 pages. That's a personal record. So yeah, feeling pretty good about that. And some of that is with 7-point font, mind you, so I could cram it all in there and not have it be even longer, but we'll get to that in a moment. All right, so within person change over time, got the do, we're ready to go. Do you all have this? Cheers. So the big picture then, these are the data that we're going to be modeling. In this example, this is from chapter 6. These are real data, actually. This is a story of practice effects. We've seen these in the ANOVA examples from chapter 3, and they're going to reappear. So this is a plot of individual trajectories. This is to what extent response time on the y-axis to a measure of processing speed improves, decreases, across 6 opportunities to practice the task in a sample of older adults. And on the whole, people are getting better, although not everyone is following that pattern. So in modeling these data, we're going to see that a line doesn't fit. These data are not described well by a linear model. So what are the options then, if that's the case? And I'm going to show you 4 types of options for nonlinear change over time. So questions then. What is the most appropriate metric of time? And in this case, it's fairly obvious, but that's not always the case. So this is the topic addressed in chapter 10 to a greater extent, hinted at in the earlier chapters. But we're talking about what should the variable indexing time be. In this case, because the reason why people are improving is the opportunity to practice, the number of times they've practiced is the time variable that we're interested in. It's going to be balanced across people, and in this case it's complete, although it doesn't have to be. An alternative would have been to keep track of the number of days in between each assessment, for instance, because people were measured maybe every 2 days, 3 days, 4 days. Rather than doing it that way, I did a time variable that reflected the mechanism, which I think is just practice. They're not going to get better unless they get a chance to sit down and do it. Just having time pass doesn't make them better. So this is something that you have to answer from a theoretical perspective as well as an empirical one. What is the right time variable for your analysis? If you're studying children, for instance, if you're studying achievement-related outcomes, time should probably be grade because that's where they're learning things as a function of the school's curriculum. If you're studying something like, changes in height or puberty or status or something that's more biological, then their chronological age might make more sense than grade as an index of those kinds of changes. So this is just something to think about a priori. And then also let that theoretical process guide you into picking a family of change. And so what type of change you're going to expect is both the function of the data as well as the process that generated the data. Back to this picture again here, we have options for what kind of change is best going to describe the saturated means. So saturated means, again, only possible when you have balanced data. That's letting each mean be a separate estimate. We're picking something that's designed to try and approximate whatever means those are. We're trying to fit a trajectory through the means and describe what kind of trajectory it is, as well as whether or not we have individual differences. So that's the other piece then. So here are the 2 baseline models for the example data that we're going to be looking at. The red line is from an empty means model. Are you stretching or hand waving? Stretching, okay. All right. So the red line is an empty means model, fixed intercept only. That model says there is no change on average. That's one end, that's the simplest possible means model we could have, one fixed intercept and that's it. On the other end of the spectrum is the answer. Those are the 6 means we're trying to fit a trajectory through. As you can see, it's not linear, it's bendy. So I'm going to show you 4 options for ways of modeling such bendy type data. That answer key only possible when you know everyone's measured on the same schedule, such that there are only 6 means possible. If you have unbalanced data, you may need to round time into convenient intervals just to be able to make a picture like this. Not to use in your models, but just to make a picture so that you're not stabbing in the dark with respect to what kind of change you're going to see. On the other side then, which aspects of change show individual differences? So which fixed effects also need random effects around them? Just the intercept and the slope, the nonlinear aspects of the slopes, for instance, or just the linear aspects. What that addition of random slopes is then doing is creating a pattern of variance and covariance over time that better matches the data. So it's fitting a time-specific prediction of change in variance and covariance over time. So it's making the V matrix look more like the data. So we have compound symmetry, which is random intercept only. Everything is the same over time. All the variances, all the covariances. Unstructured answer key model, Only possible in balanced data. All the variances and covariances get to be whatever they want. The models that we're looking at are going to be somewhere in between. So in terms of absolute fit, when we get to that, not yet. Okay, here's the same two pictures then for the variance side. So what's on the y-axis now is the variance at each occasion, not the mean. I could also make a plot for all of the various covariances, but that would take too much space. So we'll focus on just the variances because the covariances tend to follow whatever you've done for the variances. Blue line, that's flat. That's from the random intercept model. That's the compound symmetry model. That says the variances stay the same over time. What is the only type of growth pattern in which that could be true? What kind of growth pattern, in what kind of growth pattern would the variance stay the same across time? Do you know what I'm asking? Maybe? Parallel, meaning no random slopes, random intercepts only. That's the only way that the variance will stay the same over time. If people change differently, they're going to spread out. They have to. They create non-parallel lines. In the data, if you just ask SAS, hey, what's the variance at each occasion, you get the black line. And in this case, people are coming together. Variance is decreasing over time. Existing individual differences in processing speed are reduced after you give people a chance to practice. They become more homogeneous. So we know, just from staring at this pattern, that just having a random intercept isn't going to be enough. If all we needed was a random intercept on the variance side, then the observed variances would be flat, but they're not. They're different over time, and they're different in a pattern. So that right away points us to some kind of random time slope model. The question is, should it be linear or nonlinear? And if it's nonlinear, what flavor? So this is the big picture. What I want you to keep in mind is that I'm going to show you options. I'm going to show you choices. Pretend you're at Nebraska Furniture Mart and you're shopping for a couch, right? You're looking at the showroom and there's choices, 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 choices. That's what we're doing here. On the mean side, what kind of fixed effects do we need to describe the average trajectory? And then on the random side, on the variance side, which of those aspects needs to have individual differences? Which aspects of the trajectory do people need their own versions of for the model to fit well? That's what we're doing. Okay. With me so far? Now, the story here, the x-axis and the focus of the analysis is right now is modeling the effects of time. But the same choices logically apply to any predictor variable besides time. There are lots of predictors that may have a nonlinear effect where more isn't always better or less isn't always worse. So if you think about like the relationship between, say, wealth and happiness, right? Does more money make you happy, 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 happy? The literature suggests no, right? There's maybe a quadratic effect, or at the very least, more isn't always better. So if you think about the potential for nonlinear effects of lots and lots of kind, like the effect of stress on well-being, or money on happy, or let's see, what else do we have? Somebody give me something. Give me something from your world that probably has a nonlinear effect. Except Claire, she's eating. Ladies? Give me something. Food. Yes, is more food always better? At some point, you level off, right? And more food becomes worse, and then you're lying on the couch for the next 3 hours wishing you had not had that 12th piece of cake. Yes, there are lots of examples from life where more is not better. So my point is that we're talking about time as a predictor, But any continuous predictor that is likely to have a nonlinear effect on your outcome, these choices I'm going to teach you about apply to those as well. So just keep that in the back of your head. Okay, so let me go back to this, this thing here. So we have two sides of the model, right? The sides are doing different things. The mean side is describing what's happening on average. The variance side is what's happening differently across people. That means we have an opportunity to be right or wrong on each side of the model separately. So on the mean side, the question is, does the trajectory that our model creates, is it good enough to approximate the original means? So that's an absolute fit question on mean side. On the variance side, is the pattern of variance and covariance that our random intercepts and slopes create, is that good enough to match unstructured? So two different questions answered two different ways. And this is something that I did not talk about in the book, and now I wish I would have. So this is a relatively new material I'm noting up here. So given that you have balanced data, you have these two possible answer keys for each side of the model. Saturated means for the fixed effects, unstructured variance for the random effects. In theory, you should be able to do a model comparison for your model versus the right answer. And you can do that just fine when you're in REML. You keep the fixed effects the same, and you can compare whatever random slope model you end up with to the unstructured to see if it is not worse. That's what you want, not worse. On the mean side, though, you can't do that unless you're willing to switch to ML. And that's probably not a good idea. So I'm going to teach you how to get a test of absolute fit by literally filling in the missing parameters until you would get to something that looks like saturated means, and then doing a combined significance test for those missing parameters to see if they, as a set, are significantly different than 0. So I'll show you how to do that, but that's the idea, is being able to check the fit of each side separately. Because if you end up with a global test of model fit where it's significant, you need to know what to do. Like, where is the problem? Is it that the main trajectory is off, or is it the variances and covariances are off? Because you're trying to fit all of these things simultaneously. Incidentally, SEM folks, we talk a lot about absolute fit in that class, right? CFI and RMSEA and all that stuff. I know several of you have had these classes. That is a variance side, because in most measurement models, each item gets to have its own intercept, so the mean side is fully saturated. So all of the absolute fit tests in SEM are almost always just variance tests. The exception would be if you have a growth model, in which case you're back in this area where you have a means test and a variance test that's logically possible. All right, so our first flavor of Bendy, let me make this a little bit bigger here. Polynomial models. Yes, sir, that looks like a hand, not a stretch. Okay.
What is your answer here where you don't have a small number of fixed time?
You don't have a what? I'm sorry?
If you don't have such a small number of fixed time.
You mean if you have unbalanced data, or you have so much data that you can't get an unstructured model?
Yeah, you have like 50.
There is no answer key. So in that case, all you can do is try to make your model better, but you never really know if it's good enough. That's why in Proc Mixed, it doesn't give you the same automatic tests of absolute fit that you get in SEM programs, is because Proc Mixed doesn't assume that you're in the situation with balanced data. In that case, you just got to do the best you can. Pictures, I would literally plot means and variances from what the data say versus what the model says, because even if you can't get an unstructured model to estimate, you can always run like Proc Core and ask for the covariance matrix, and you can get the variances just from the data, and you can see how your model predicts them and see where the holes are, and that will help you try and fill it in, but you'll never really know if you're right. So hope or pray. That's the positive answer. The negative answer is, well, if you can't test absolute fit, then you never know if it doesn't fit. Which can be a blessing in disguise, because then you can't be wrong. So that's a whole nother question. But yes, pictures, that's what I would do. That's the best case. All right. So Bendy models, by far the most common option that you will see in the literature is the polynomial approximations. These can be decent when you have maybe 3, 4, 5 occasions. They are somewhat problematic though, and I'll show you why that is. But they are the most common, so I want you to know about them and know how to interpret them. So what am I talking about polynomials? I'm meaning squared, cubed, fourth versions of time. So if I just put in time, that's a linear model. Time squared is a quadratic model. Time to the third is a cubic. Time to the fourth is a quartic. Time to the fifth is a quintic. Then a sextic, septic, I think octic, nontic, ninetic. What's 9? Deca? I don't know, but I think since 7 is septic, I think that's a good sign that like you're done right there. That's a bad one. In practice, the highest I've ever seen actually yield something useful is cubic. I think if you have to go past cubic, polynomials is not going to be sufficient. I think you need something else instead. Generally speaking, in balanced data, you can only have polynomial slopes up to the number of occasions -1, and that will create a saturated means model. So the -1 is because you always have a fixed intercept. So that's where the 1 comes from. So that means if I had 3 occasions, how many means do I have? Let's see if you're listening. If I have 3 occasions, how many means? 3, yeah, we got that one. That means I can have fixed intercept, fixed linear, fixed quadratic. How many fingers am I holding up? Yeah, I'm too short, sorry. 3. So that's 3 means, 3 fixed effects. How well is that going to fit? Not a trick. If I have 3 means and I put in a fixed intercept, fixed linear, fixed quadratic, 3 things, how well is that going to fit my 3 means? What's 3 minus 3? 0. If I have 0 degrees of freedom, how well is my 3 going to fit my 3? Perfect. Yes, I swear I'm not trying to trick you. I will warn you if I'm trying to trick you. Yes, perfect. So it's a rearrangement. There's no point, really, to fitting a fixed quadratic model with 3 occasions. It's just spitting the 3 means back at you. It's not summarizing, it's just rearranging. Same would be true with 4 occasions. If you picked up a cubic, then you'd have intercept, linear, quadratic, cubic. 4 and 4 leaves no degrees of freedom to be wrong with. So you're looking for less terms than all possible in order to have a useful model, generally speaking. So in people's articles and in other classes and workshops that I've taken, punting on quadratics seems to be a time-honored tradition because they're just too hard and they're not interpretable, so we're not going to even talk about it. I'm going to break that right now. Quadratics are super easy to interpret once you know how to do it correctly. The correct way to interpret a quadratic is to remember the number 2. A quadratic slope describes twice how the linear rate of change changes per unit time. Yep. To describe how the linear effect of time changes per unit time, you multiply the quadratic by 2. That's written right here. So for instance, if I have a fixed linear time slope of 4, and it's paired with a quadratic slope of 0.3, what that quadratic does is make my linear time slope more positive by 0.6 for each additional unit of time. Twice the quadratic is how the linear slope changes per unit time. I'll say it again. Twice the quadratic is how the linear slope changes per unit time. time squared is an interaction term. It's time by time, right? Do you remember the 4 kinds of interaction terms? This is like maybe 6 weeks ago. Remember? What are the 4 kinds of interaction terms possible in the world? I'll give you one of them. More positive. More negative. Less positive. Less negative. That's it. There's only 4. Since a quadratic term is an interaction term, the same applies. A quadratic will make the linear slope more positive, less positive, more negative, or less negative as time goes on. That's it. Now, why twice? I'm going to give you 2 different explanations, and hopefully one of them will appease you. Anyone remember calculus? You're like, oh yeah, I took that like 20 years ago, didn't I? Well, if calculus is more recent to you than 20 years, I will give you my calculus reason. What we're actually talking about is the second derivative of a function. So in taking derivatives, the rule is that the exponent comes down in front of the term. So if I have the first derivative of this function here with respect to time, the constant goes out, t to the first drops down and t goes away, the 2 drops down to be t, the second derivative then gives you twice that. So that's one reason why, the twice. If calculus was 20 years ago for you, like for some of us, here's the other reason. Because of the rules of interactions, the twice shows up. So let's look in this little box here. Is my mouse working today? Sort of. If I have this model right here from regression, main effect of x, main effect of z, and an x by z interaction term. That x by z interaction term is doing 2 things simultaneously. It is changing the effect of x as a function of z, and it's changing the effect of z as a function of x. It's doing 2 things, 2. In our model, it's like we're missing what z was. I have an interaction term, but I only have one of the 2 main effects. So whatever it's going to do to the main effect, it has to do it twice because there's no other main effect for it to do it to. All right. Does that one better? The third answer is because I said so. Because math, right? Math don't care. It's just the way it is. So it's one of those rules that you have to memorize, like 10 to the 23rd moles in a whatever, right? 6.02 times something, 215 Kelvin. There's all these like things floating in my head that I memorized at one point in time. Just store that on your list. Twice the quadratic is how the linear slope changes per unit time. Twice. So here are the 4 kinds. This is a figure from your textbook. I forget which one, but it's in the beginning of chapter 6. The top left pattern here shows a linear slope of positive 4 paired with a quadratic slope of positive 0.3. Now note the x-axis here starts at 0. When you have an interaction term, what is true about the main effects? Simple versus marginal. Remember this? If you have an interaction term, the main effect is its effect specifically when the other predictor it's interacting with is 0. In this context, then, it's not okay to talk about the linear slope. We have to talk about it as a simple main effect, as a conditional main effect. So now we say the linear slope when time is 0. Because the time variable is interacting with itself. The whole point of a quadratic model is that the linear slope changes. You would have a different linear slope at each occasion. So this slope of 4, this is my best PowerPoint rendition of the line that's tangent to the curve here. That is this 4. It's the instantaneous linear rate of change at time 0. It's the linear slope at time 0 specifically. What happens to it? The quadratic coefficient of positive 0.3 makes it more positive by 0.6, twice the quadratic, at each subsequent occasion. So the linear slope goes from 4 to 4.6 to 5.2 and so on. So if the linear slope and the quadratic slope are of the same sign, they work together to create some kind of acceleration. The same is true down here, except it's negative. Here's a negative linear slope paired with a negative quadratic slope in the bottom right. And here, the quadratic slope is making the negative linear slope more negative by twice the quadratic. So we go -4 to -4.6, -5.2, and so on. So I'd call that a deceleration, or excuse me, an accelerating negative curve, acceleration negative. The off panels here, the top right and the bottom left, show opposite signs. So the top right is positive linear slope at time 0 paired with a negative quadratic. It's going to slow the curve down. So I would say the linear slope of 4 at time 0 becomes less positive by twice the quadratic. So it goes from 4 to 3.4 to 2.8 to 2.2 and so on. I would call that deceleration, going up less over time. Last but not least, bottom left, negative linear paired with a positive quadratic. I would call this going down less over time. -4 to -3.4 to -2.8. So you can't tell what pattern it is based on just the quadratic being negative or positive. You have to know what the linear slope is too, and where the linear slope is as well. Just as you learned in regression, if you have an interaction term in the model, the main effects stay with it. The same is true here. Even if the linear slope itself becomes non-significant, once the quadratic is included, both stay, linear and quadratic. The quadratic is only the quadratic if it's above and beyond the linear term. Okay, how are we doing? So let's think about what these models would say should happen as time goes on. Let's look at the top right picture. Let's say that this is an achievement as a function of time. Kids learn more and more, and eventually their learning starts to slow down. What does this model say is going to happen at time 6, 7, 8, 9, 10? You would think they come back down. They get dumber as time goes on. It's going to create an upside down U. Yeah. The same would be true over here on the top left. If you follow this backwards in time, they would form the other half of the U. And that's why people, and I'm one of the people in some cases, don't like these models, is because they're theoretically like icky. Because yeah, Amy's like, it should stay up there, right? No, that's not what the model does. So from a theoretical perspective, it doesn't match like what should be going on when you think about learning or improvement. It is rarely the case that learning goes away and you end up right back where you began. If you want the function to get up and stay up and stay up there, you need some kind of model that has an asymptote, a nonlinear model that says explicitly what the optimal performance would be, the lowest and the highest. Those are coming. I will also show you a way to make these pictures a little more palatable by taking log time and then looking at the linear and quadratic effects, which is going to greatly slow down this U-ness of the curve. But yes, if you're looking to approximate nonlinearity for just a few occasions, and you really don't care what's supposed to happen after the study's over or before, then these models are fine. If you want something theoretically more meaningful, this ain't it. But it's very, very common. So what's a quadratic? Twice, yes. Twice the quadratic is how the linear slope changes per unit time. It's half the rate of acceleration or deceleration. And you are going to have buku homework problems on this idea, by the way, because I will not rest until everyone on Earth knows how to interpret a quadratic effect. That's going to be my goal. You can put that on my tombstone. So conditionality then, as we add these quadratic terms to the model, the lower order terms are going to change because they're going to mean something different. So just as we saw earlier, if we have a fixed intercept only on the mean side, that's the grand mean, the mean of the means. Once we add fixed linear time, it becomes the expected mean at time 0, and the linear slope is unconditional. When we add quadratic time, the fixed intercept still has the same interpretation. It's still the expected mean at time 0, but what expected is different. It's expected based on a bendy line instead of a straight line. So the estimate will change. The interpretation of the fixed intercept is the same. Both the estimate and the interpretation of the fixed linear time slope are going to change because it becomes specific to time 0. It's no longer the average rate of change, assuming constant change. It's the expected instantaneous linear rate of change at time 0. The quadratic is half the rate of acceleration or deceleration, and it's constant across time unless you were to put a higher order term in the model. So what if I added fixed cubic? Can you guess what's going to happen to fixed quadratic? Stay the same or become at time 0? If I add fixed cubic time, at time 0, exactly. So all the lower order stuff becomes conditional on the higher order stuff on the mean side, and the same is true on the variance side. So if we can have fixed quadratic time, that is allowing people to have changes in their linear slope, we can have individual differences in the extent to which people change in their linear slopes. So we can have random intercept, random linear time, and random quadratic time. That would look a little something like this. So here's my level 1 model. How many betas are in my level 1 model? 3, not a trick. That means how many level 2 equations do I have? 3, yes. What are the Y-looking things here? What letter is this? Gamma, yes. What are they? Fixed effects, yes. So they are the average for the sample of whatever the beta means. So that means gamma 0, 0, the first one, that's my average intercept. Gamma 1, 0, the second one, is my average linear slope. Gamma 2, 0 is my average quadratic slope. The first number of the subscript on these gammas says which beta at level 1 it's predicting. So it's gamma O because it's beta O, it's gamma 1 because it's beta 1, it's gamma 2 because it's beta 2. The second subscript is which order in the level 2 equation it is where we start counting at 0. So the second O means that it's the fixed effect for that beta. Then we have the U's, right? U is how far off yours is from everyone else's. How far off are you, U0 intercept? How far off are you, 1 for the slope? How far off are you, 2 for the quadratic slope? Each of those has the same idea. Red, fixed, what happens on average? Blue, random, how far off are you? So how many random effects are in my model here? Not a trick. 3. So how many ways do people differ from each other, need their own of something? 3. So how many piles of variance are up for grabs at level 2? 3. How many piles of variance are up for grabs in my whole model? And don't say 3. Or 2, or 1. Four. Yeah, E sitting up there. 4 piles. E is why are you off your line today? U0 is why did you start out so much slower than everyone else? U1 is why are you changing more slowly than everyone else at time 0? And U2 is why are you more bendy than everyone else? So we need 4 occasions at a minimum to fit this model. On the fixed side, the rule that I gave you for fixed slope related to time is n-1. On the random side, it's n-2. The 2 is because we're not counting the random intercept and we're not counting the residual variance. So we're talking about how many slopes related to time can you have be random. In this case, if you want to have 2 slopes related to time be random, the linear and the quadratic, you need at least 4 occasions to pull this off. All right, so here's the sequence that we're going to go through. And we're going to go through it again because it's going to review what we did previously. Empty means random intercept. That's the simplest model we would ever entertain for longitudinal data. We do that to check the interclass correlation. Here's a review. ICC is proportion of variance that is within or between? Between. So if I have an ICC of 0.99999, what does that mean? Game over. That means I have no longitudinal data. It's all between. So that's step 1. Do you have longitudinal data? Step 2, fixed linear. Given that we're adding a fixed effect, we can stare at the p-value. That means use the wall test that's provided. Does that linear trend need individual differences? That's random linear. That's a model comparison, -2 log likelihood on 2 degrees of freedom. Then we'll add fixed quadratic. If it's a fixed effect, then we check the p-value. And do people need their own quadratics? That's random quadratic. That's random variance side change. That's model comparison. And in this case, it will be 3 degrees of freedom because it's random quadratic slope variance plus the covariances with the stuff that's already there. So we're staying in REML for all of this. You ready? Page 1 of 39. Yes. My very first time teaching actually was teaching this subject at Penn State as a postdoc. Everybody went on sabbatical at the same time and they had no classes, so they let me teach. And it turns out I was a god for like 6 months because I had handouts. Because everyone else showed up with chalk and I showed up with paper, and that made me awesome. So I've internalized this, and I figure I'm even more awesome if I have a 39-page handout than a 15-page handout. So you'll have to excuse me. I'm just, it was a formative experience. But what I want to leave you with is enough resources to where if you come back to this 2 years from now, you will have a shot at being able to follow your own notes. I figure the less you have to write down, the more stuff I give you, the better off you are. So it's for your own good. Plus, you don't even have to print anymore, right? I know some of you like paper still, but I hate paper. So it's all electronic. So these data then are available for you to play with. I have all of the syntax for all of this as well as the output that it creates for download on the class website, as well as the Excel sheet that goes with all of these things. Session is my categorical indicator of time. So that's going to be my level 1 ID variable that I use to structure the R matrix. Time 1 is what I am calling my time variable. So it's having the constant at which 0 is indicated as part of the name here. So that's what time 1 means to me. It means time centered at 1. So session runs from 1 to 6. Time 1 runs from 0 to 5. Here's my answer key. Answer key on both sides, which is possible because these are balanced data. Let's review the proc mixed code here. Note that I am using a file, like an abbreviation like file save called data file here to note the data set name. So if you want to steal my code and use it for something else, just remember to change what your data set is called up here. That way it will work. Had some questions on homework, so I'll go back over this. Cove test is an option that gives you standard errors on your covariance table. No CL print suppresses extra output related to the class statement that you don't need. It details you are going to need, so please mark this. I have it in bold here. I couldn't come up with a font big enough. When you do your homework, make sure that you are taking your -2 log likelihood values from this table called iteration history, because I'm asking for them to 3 decimal places, and later in the output it only prints it to the 1st decimal place. So you need this it details to get this table, and in your output it's going to be a lot bigger. It has all of the covariance parameters in it, and then it has the log likelihood towards the end of it. Namelen equals 100. By default, SAS only prints the first 20 characters for your predictor effects, and if you have interaction terms, that can start to truncate things so you can't read it anymore. So that just makes it use 100 characters, 100 being an arbitrary value. And IC, that prints the info crit table. So if you don't have that IC in your code, then you won't be able to use my fit test macro that relies on that table. And then method equals REML controls whether you're in REML or EML. So on the class statement are my 2 ID variables. Person ID keeps track of who is who at level 2. Session keeps track of which occasion is which at level 1. Response time, or RT for short, is my Y, my outcome variable. So note that I have session in the model line and on the class line and on the repeated line and on this one. The fact that it's on the class statements is telling SAS to do what with it? Dummy code it, make it categorical. It's saying, hey, can you just like treat that as a categorical variable and make all my contrast for me? Cool, thanks. So I'm creating a saturated means model. It is going to give me a fixed intercept for the highest numerically or last alphabetically on this variable and 5 mean differences. If I want to get what the actual means are predicted to be, that's why I write this ls mean statement right here. So that does the math to take the fixed intercept and add the contrast to it to get the predicted means at each session. Excuse me. What's my repeated line doing here? Normally, yes. But do I have a random? I don't have a random line. That means it's both. So it's an R-only model of what kind? Type equals what, folks? Unstructured. Everything gets to be what it wants. That's why we don't have a random line. So this is going to give me the answer key for what the variances and covariances are over time that my random slopes are going to try to predict. And here it is. So note on the diagonal are the variances. That's what I made the picture of in the PowerPoints. Variances are decreasing over time. Correlations vary over time as well. Top of the next page is my info crit table. The IC code on your proc mix gets you this table. The first number is your -2 log likelihood to only the first decimal place. Number of parms I want to make a statement about here. 21. In this case, we are using REML. That number refers only to the number of variance and covariance parameters. It isn't counting the fixed effects. So in total, I have 21 variances and covariances on the variances side. How many parameters do I have on the mean side? And feel free to count the number of rows with information on this table. 6, yes, that was almost perfectly timed. Yes, 1 fixed intercept and 5 mean differences. That's what I got by putting session on the class statement and in the model. So the next question here, this thing. This was a homework question from last time. What does that F tell us? That's my multivariate walled test for the effect of session. Or in English, you can think of it as a model comparison. You can think of it as a model comparison. It's comparing this saturated means model against a model, the empty means model, which is a fixed intercept. In English, there was a significant omnibus main effective time, comma, F equals blah, 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 comma, such that. What? You always need the such that, right? Because that's the part people are going to highlight. Yes, response time varied across time. The 6 means are not the same. The end. Now, just from this F, do we know if people go up or people go down or what? No, they're not the same. That's all that tells us. Flavor of not the same, we would have to get a sense for right here. And these are the means that created the picture in your PowerPoint. On average, yes, response time is decreasing over time in some kind of nonlinear way. I can't say anything more specific than that right now. But this is the answer key. This is what we're trying to approximate with fewer parameters. Bonus question here. If I were to estimate the same model in least squares, I would get the exact same answers back because REML is least squares if you have complete and balanced data. But what would you call it if we have this saturated means unstructured variance model in those words in least squares land? Anyone remember? What kind of ANOVA is this? Some kind of, I'll give you acronyms here, RM, repeated measures, there's 2 kinds. Which kind is this? Multivariate, yes, this is a MANOVA. That's what this is. This is the MANOVA approach to repeated measures. So it can never be wrong, but it can be unestimable, and it can be too complicated. So we're looking for something that does as good a job with fewer parameters. So we're starting at the bottom now and working our way up. Simplest model, empty means random intercept. This is the worst model we would consider for longitudinal data, but we want to get an intra-class correlation and give us a place to start. So empty means on the model line, no predictors. Fixed intercept is there by default. We picked up random again. Each person is getting a random intercept. That means that type switches back to VC, and that creates this pattern right here: variance components, equal residual variances, no covariances at level 1. At level 2, we have a random intercept variance. Yeah. Looks like my spacing is going crazy on here. That's all right. Here's my model. How many parameters am I estimating? Let's count them up. On the mean side, how many fixed effects? Not 6 anymore. We're back down to the simplest model. How many means parameters? 1 fixed intercept. Now, how many variance parameters? Say your number again, Aaron. 2. What are they? Yeah, U variance, U0 variance, random intercept variance, and E variance, level 1 residual variance. There we go. So that model is my compound symmetry model. So there's my V matrix that I get from putting level 1 and level 2 back together again. If I take that covariance and I turn it into a correlation, special name, ICC, intra-class correlation of 0.8173. So 82% of my variance is what kind? Level 2, 82% of my variance is random or residual. If 82% is level 2, then 82% is random or residual. Random. 82% is U0 variance. 82% is cross-sectional or longitudinal? Cross-sectional, yeah. So 82% of the variation in response time would have been there if I had done a cross-sectional study in the first place. I've picked up an additional 18% by making them do this task six times. So on average, it takes people about 1.7 seconds to do this, 1770 milliseconds. So going through the polynomials then, starting with linear. So this is a review of last time. We are in REML. I am introducing a new predictor variable in the model line. This is my time variable. What is the difference between time and session? Which one is categorical and which one is continuous? Session is categorical. Time is continuous. If it's not on class, the default is that it's continuous, meaning I'm asking for a slope through time. And I know that it's a linear slope because it's time to the first, as it were. Let me go back for a second and point out something I forgot to mention. In the empty model, I have saved the covariance parameters table. So I've saved the table that lists the random intercept variance and the residual variance, and I've called it cov empty. I have done the same thing in our new fixed linear model. I've saved it as cov fixed lin. Again, those are my names. And I've saved the infocrit table as fit fixed lin. So I'm saving these pieces of information for future reference so that I can compare them against other models. I am also writing estimate statements to ask SAS to tell me what this fixed linear trend predicts the mean at each occasion to be. So you can think of these as several different words that all mean the same thing. I'm asking for a conditional mean. I'm asking for an intercept. I'm asking for a predicted outcome. Any of those words mean the same thing. At time 1, what is response time predicted to be by a linear trend? At time 2, what is it predicted to be? So I've included in the label here session and time so that we can keep track of what this means. So at session 1, time is 0, and that's why I fill in a 0 here for my time variable. I have an intercept for all 6 of them because your predicted mean starts with the fixed intercept, and then we add to it the effect of the time slope. And you get as many effects of the time slope as you have occasions by then. So this is the value that would multiply your slope coefficient to get you a predicted value. Okay. Any questions on that? All right, so let's see what happens. So going down to the fixed solution for fixed effects, that's where my new term is. This is a fixed linear slope, so how do I know if it's significant? Stare at the p-value, Wald test. Survey says, yeah. The coefficient is -52. Since we're out of time, I'll put that in a sentence for you. For every additional session, response time decreases by an average of 52 milliseconds. So if you look at these predictions down here, each of these numbers is 52 milliseconds less than the one before it. So people are improving on average. This model predicts that everyone's improving the same though because it's only fixed linear. And I'm using my pseudo R-square macro to calculate the change in the variance components between models, and I see that my residual variance went down by about 21%. So 21% of the 18% is explained by a fixed linear slope for time. 18% from the 1 minus ICC that was there in the first place. So we can go back over that next time. All right. Questions on that? Then that's where we will pick up on Wednesday. I shall see you then, hopefully.